going to be looking mainly at the question how we can reduce the cost of energy right now with the tools we already have. And joining us to moderate this very session is none other than Robert Stöcker, partner at ENO. Here you go. That's the clicker. Fantastic, have fun.
Thank you. All right. Hi, everyone. I think it's a bit of movement, but I was told we need to catch up a bit on time, so I would say let's get right into it. So I'm Rob Stöcker, partner at ANU, and we are a early-stage venture capital fund financing the energy transition and the industrial transformation. And today and the next hour, we're speaking about something that doesn't get enough airtime in the industry, and that is the energy system cost. So we spent the last 15 years reducing the cost of a solar panel or a wind turbine by 90%, which is great, but that was, inverted commas, the easy part. Producing the cheap electron is no longer the bottleneck, but the hard part is keeping the cost of the entire system down. So everything that sits around it, storage, recycling, grid services, materials supply, and resilience. Over the last decade, the levelized cost of electricity was a useful KPI, but today, as said, we need to focus on the system level cost. And I was told to anchor the sessions a bit, and I would like to do this by adding 3 numbers to keep everyone a bit engaged. The one is Europe pays roughly 2 to 3 times more for electricity than the US. 2, grid services in Germany can cost double-digit billion euros per year. And number 3, more than 70% of critical minerals in a battery still travel through China. That last one especially always blows my mind. But none of these problems get solved if we add another solar park. However, the speakers that we have on stage today are the ones that are going to bring these solutions. So in very brief, the 4 speakers are Anaphyte, who's pulling the costs out of how we make batteries. Scilab is closing the loop on the materials that we put into them. Skeleton Technologies is making the grid behave when the wind stops blowing. And Terra Quantum is making sure that none of the before get switched off when they're being attacked. So we have production, recovery, balancing, and security. These 4 layers represent the system-level pathways of reducing energy system costs. So I would say, enough from my side, let's get into it. Our first speaker, Joe, please help me welcome Joe Stevenson, CEO of Anaphyte.
Thank you very much.
Sure.
So thank you very much indeed. It's a brilliant introduction, bringing all of these themes together. This is a very, very large topic. So I am talking about hardware and the hardware of energy storage, the storage that is needed to balance supply and demand, that is needed to enable new, faster connections to the grid, and specifically about the battery cells. Battery cells made of LFP, lithium iron phosphate. So why is LFP important for Europe, important for the whole resilience and cost of the energy system? Is this? There we are. Okay. So BESS, Battery Energy Storage Systems. In the energy network, these are just what these large banks of cells are called. And this is almost entirely an LFP story. The cells that are used for this are made with a cathode composed of lithium iron phosphate. And this is important also because, as you just mentioned, this is almost entirely a Chinese story. So 98.8, I think, currently % of lithium-ion cells comes from China. And if you look at the upstream supply chain and the downstream supply chain, it is also dominated by China. Now, these are not inherently scarce minerals. This is lithium comes from many places in the world, iron, phosphorus, but the supply chain and the cost is dominated by China. So there you see the cost advantage of Chinese production, $60 per kilowatt hour of cell, against the European cost. And the European costs are not in the materials. You know, when we are talking about very expensive battery chemistries, a lot of it is in the metals. In this, it's not. It's in the cost of energy, the cost of the capital. And what we're trying to do at Anaphyte is make Europe competitive, bring European production to viability by changing the way that these cells are made. So there are two ways to make an electrode. The way that everybody does it now is this long line on the top. You take your LFP and your other ingredients, you mix it in solvent, and then that is like a paint, like an ink that is coated onto the metal foils. Now, as soon as you have made that ink and deposited it, you must remove the solvent. And that solvent removal step is this big long oven. That's 80% of the equipment, it's 80% of the floor space, and it's also 80% of the energy consumption of this whole process. So what we do at Anaphyte is we do the green one down below. We are making mixtures of the important materials, but we are applying them without solvent. And because we are not using solvent in the coating process, we do not need the oven, we do not need the space, we do not need all of that energy. So that's the key thing about our technology. It enables this dry coating process. And what that means at a factory level, it means less equipment, smaller footprint, but importantly, at a factory level, the whole gigafactory, 50% of the energy. So by moving to this process, we are removing the energy demand from the factory itself, and we are taking out a lot of the cost. So 20% of the energy of the cell cost was energy. If you reduce that by 50%, you have removed 10% of the whole cell cost. That is what this process enables. So there are other benefits to what we are talking about as well. We are talking about accelerating deployment and commissioning timelines. The process itself is inherently smaller and simpler. It does not require toxic solvents for the coating process. These toxic solvents are a big problem, particularly in Germany. To build a factory using these solvents requires a lot of permissions. And the number of sites, the number of places that you can build the factory that needs that much power are very small. So if we can remove the solvent, we can make a smaller factory that requires less power. We then have more opportunities to build facilities more quickly. Our technology is this green piece in the middle. You will see that at the beginning, the materials, the powders, and all of the end to the finished cell are the same. What we have taken out is the piece in the middle, and particularly the oven drying. Now, there are other ways that this can help. If we change to the new coating processes, we can make electrodes with a higher capacity. If you imagine making a very thick layer of paint, it's difficult. You want to maybe have to do it several times. If you're using dry powders, it's much simpler to make a thicker, higher capacity electrode. And because we are controlling the structure of what we are doing, because it's dry, we can then introduce a better structure into the electrode that means that we still have good power handling. So the usual compromise that you get in cells between, do I want a lot of energy or do I want good power? The trade-off is still there, but it's not so extreme with this technology. And we can move to higher capacity electrodes, which increases the throughput of the factory, which then improves productivity and also those energy savings even further. So this is why Europe and European energy resilience needs dry-coated LFP. This is not a simple technology. It's something that they haven't shown that they can do in China yet, although of course they're working on it given these benefits. But the way that we can make it work for Europe is then by reducing those costs in the cell plant by moving to a much more energy efficient and smaller process, and then by improving the product as it goes through the process. And that's what the Anaphyte dry coating process delivers for Europe. Now, this is a deep tech conference, so I have to include some technology. I don't know how many electrochemists there are in the room, but just to show that we have demonstrated the electrodes are robust. This is very, very difficult with LFP. It's easier with anodes, it's easier with NMC. This is very difficult. We can laminate good, strong electrodes that can be processed into cells, and when we make them into cells, they have very good class-leading performance in our testing and in our customers' testing. So we can make them as they're made now, but then more energy efficient and with higher performance, fewer performance compromises. So just to summarize, what do we deliver for Europe? We discover a route to cost-competitive European manufacturing. This is not something the Chinese cannot do, but it's something the Chinese do not do. So we are all starting from the same place as a way to try to get to this new technology that will remove some of the structural uncompetitiveness of Europe, like high energy costs. We can make better performing cells here. Cell performance goes in big steps, but a lot of it is incremental. And this is an opportunity to open up that innovation space for incremental performance improvements. And then finally, it's a way to get factories, gigafactories, to make these cells built within European permitting restrictions and within the constraints of, ironically, the European energy network. So that's what we're working on in Anaphyte. We do a lot of work in vehicle batteries as well. That's where we come from. But now we see this LFP work as being increasingly important for our future and for our contribution to the European energy system. So I will be here around and happy to answer questions now or later, according to Robert's interest.
Hi, is there any impact on the thermal performance with this manufacturing method?
No.
Oh, cool.
No. Nothing is ever a drop-in, but they do perform pretty much exactly like cells made in a conventional wet coating process. The only compositional difference is the thermoplastic binder that's used to hold everything together.
Sure. Hi, thank you for the lovely presentation. I'd just like to know, what is the TRL for this kind of technology, firstly? And have you done any pilots, or are you doing any pilots soon? And what do you think is likely going to come out of those?
So the TRL for this process is TRL 6, but we're not a cell maker. We work with cell makers. So we are reliant on our customers then to test these in large format cells. We do all of our testing in relatively simple cells. That TRL then is lower. The challenge for us, I think we've demonstrated the capability of the product performance. Our challenge now is to scale out the process to demonstrate speed and yield, because if you cannot show high yield at high speed, you do not have a viable industrial process. That's the next fundraising round for any of the investors in the audience.
Yes.
For the last point, if you want to scale it, I think you developed a great technology. Nevertheless, you also need to scale it, so therefore we need the right machinery. Is this part of your scope, or are you expecting that big system integrators are jumping in and doing this or licensing your technology? What's your plan?
So there are two processes here. There is mixing the powders. The machinery from that generally comes from the food or the pharmaceutical industry. They like dealing with sticky powders. The coating technology is roller-based, and it comes from printing. So Falve's partner for this technology is Koenig & Bauer, who make printing presses. So they are different industries, but the types of machines are all very familiar. We have to run the machines ourselves. We have to know how you set them up, how you specify them, and how you operate them, but that then becomes a transferable technology package. We believe that the big cell makers will want to run this process in-house. It's an important part of the value of the whole cell-making operation.
All right. Thanks a lot, Joe. Everyone give it up for Joe. I'll take this very much. Thanks. Yes, and obviously if Anaphyte is successful at scaling these dry-coated LFPs, then this takes out a meaningful cost chunk, how batteries are being produced. But the unit economics of a battery get really juiced up if you can do it twice. Once when you build it, and once when you recycle it and put it back into the system. And this is what the company, Scilab, is working on. And please welcome our next speaker, Julian Engelberger.
Thank you very much. Good afternoon. Continuing to work in, or to speak about the ecosystem of batteries, but maybe first taking a step back on where we stand as a European industry. I mean, we have discussed fusion just a bit ago and how much more electricity we will need over time. And we're also seeing a huge trend towards electrification. In China, more than 50% of the cars are now electrified, up from about 5% of the cars in 2020. So a huge electrification trend, and the game is changing. The rules of the games are changing. If we are looking at the company Kodak, and I guess most of you, since we're at a tech conference, most of you know the innovator's dilemma. That has been wonderfully described by Clay Christensen. Kodak faced the question, sacrifice their analog film business to play in the new and upcoming digital photography, or defend the highly profitable analog film business. They chose to play according to the old rules and went bankrupt in 2012. If we are looking into electrification, that is pretty much the state of the industry. We are currently still in many areas playing to the old rules, playing to the combustion rules, and we are not ready for the electrification. Why are we not ready? The rules of the game are fundamentally changing. If we're looking at a vehicle powertrain, an electric vehicle powertrain has 90% fewer moving parts than a combustion engine powertrain. At the same time, an electric vehicle powertrain has 20% more, higher share of critical minerals than an ICE combustion engine powertrain. Meaning, in the past, we benefited from engineering excellence. That was our moat. That moat it's not gone, but it's much less relevant in an electrified industry. In the new electrified industry, it's the critical minerals access that we need to master. And unfortunately, we're not ready for that. If we look, and Joe, you essentially showed similar numbers. This is more or less the entire value chain. I think you showed essentially that bar with your presentation. If you look across the entire value chain of battery manufacturing, from the electric vehicle to the mine, and you look at ownership of the assets that are in the global market, pretty much everything is red. That is China, owned by China or by Chinese companies. And then there's South Korea and Japan, the two other biggies. And apart from that, there's little to nothing. We are not ready for the mode of the future, the access to critical minerals. That needs to change. We are out there to change that. Scilab was founded, the research of Scilab started in 2016 by our founders, by Lilian, Gideon, Paul, and led to the development of our core technology, which is a hydrometallurgical recycling technology. Why do we need to do that? The game is also different in Europe versus China. You just mentioned it, Joe, from a electrode coating perspective. It's similarly for the upstream value chain. The rules are very different. Strong chemicals, use of strong chemicals, very costly in Europe, very difficult to permit in Europe. So technologies, the success factors for technologies are very different in Europe compared to Asian countries. Started out at RWTH Aachen with technology development. Now, having our demonstration plant in Aachen up and running, and set out to prove that the technology worked. Actually, it does work. We have proven that. We have just last year and this year we have worked together with our strong partner Porsche to create battery-to-battery recycled batteries, so really closed the full circle, and have produced cars that are driving. Unfortunately, the batteries are have still been produced in other countries of this world, but at least the materials, the critical minerals, were produced in Aachen. Now we're taking the second step. We are scaling that up to industry scale. That's of course, and Mr. Fleischer from Siemens just mentioned that it's building up an industry. It's the change of the supply chain is a beast in itself. We have kicked off our project, our first of a kind factory project in Dormagen, 2024, with Hendrik Wüst, the Minister President of North Rhine-Westphalia. And we are in the middle of building that factory in Dormagen. This is unfortunately still a rendering. We are heavily working on that part of the factory currently, progressing well. This will be the first industrial scale battery recycling facility in Europe. And that will be able to cover both NMC, which is currently leading and dominating the European market still, and LFP, which is gaining rapidly market share due to battery energy storage systems, as we just heard, but also due to electrification of more volume segment electric vehicles. Scilib needs to be the answer to Europe's critical mineral access. We have the big advantage that every electric vehicle that is being built and that is being sold in Europe is our mine. We don't have the mines, the big nickel and cobalt mines in Europe. We also barely have lithium mines in Europe. Every vehicle that is being sold is a mine for us. We are ready to exploit it. We will be able to circle back from the battery to the raw material. We discussed earlier about costs of energy systems. Cost is certainly one thing, and we're obviously focusing on improving cost positions. But at the same time, just having the pure access to minerals is an even greater challenge in the current geopolitical environment. We see that supply chain risk is more and more detrimental to business performance and to business continuity. So from our perspective, it's almost more of a sovereignty topic than a cost topic to do recycling in Europe, despite it needs, of course, to be a business case in Europe as well. And lastly, why cannot Chinese companies just do the recycling in Europe? The technology requirements are very different. The technology environment is very, as I mentioned earlier, it requires completely different success factors to be profitable and to be permittable in Europe. So from that perspective, we have the technology that we need in Europe, and we are currently industrializing it. Nevertheless, it will not work with, apologies, it will not work with us alone. We need the ecosystem. And that requires a lot of work. That requires a lot of partnering within the industry, and we're heavily into that. And if you have any contact points where you feel like it might be relevant, please reach out, please connect. We are more than open to make that ecosystem, that European battery ecosystem work. The value chain the circle needs to be closed within Europe, otherwise it's going to be nice, but for sovereignty, from a sovereignty perspective, it's going to be much more effective if we can close the circle. At the same time, we also need to create the ecosystem from an investment perspective and from a regulation perspective in Europe. Also there, we need, to some extent, export bans for black mass. We need to close. We need to politically and from a funding perspective incentivize keeping our raw materials, our critical minerals in Europe. Otherwise, we will not be able to gain that or to create that moat around Europe based on critical minerals access. With that, we always say, mine once, recycle forever. Let's close the loop in Europe. Let's keep the critical minerals here once we have them, and let's build our industry based on that, so that we and our children and grandchildren can still benefit from industry and not just our past. Thank you.
All right, we have time for one question, if there is. There we go, man. First come, first serve.
Thank you. What is the drop in performance after recycling and the pattern after several recyclements, or are recycled batteries indistinguishable and have equally high performance? And second, a related question, for Porsche, for instance, do they consider labeling that the car has a recycled battery, or they want to keep it, again, indistinguishable?
Yeah, I think yeah. Good question. So first, our output materials are as good as any primary materials. They are indistinguishable from a specification perspective with regards to impurities, with regards to concentrations. It is the same material that goes into the battery. And from that perspective, there's no difference with regards to the battery performance. You might read something different about direct recycling, where you don't go the complete loop, but rather stay within essentially the battery factory and close the loop. But with the full recycling, where you really close the loop from the end-of-life battery back to the MHP, to the cobalt nickel sulfates, the lithium carbonates, there's zero difference. Porsche and all the OEMs, they need to fulfill the European Battery Directive, and that requires some minimum levels of recycled content. Over time, that minimum levels increase. And beyond that, there might be some marketing incentives if customers are willing to pay more for a battery with more recycled content. I wouldn't bet on that. I would rather say we as recyclers, we need to be cost competitive with primary material, and we can be cost competitive with primary material. So from that perspective, it's our job to be competitive enough to make sure that our adoption goes beyond the minimum required level. And that's what we're on to.
All right, thank you, Julian.
Thank you very much.
Okay, now we move from the cell to the system around it. And I think one anchor that I want to share is that storage is not just one product, it's made up of an entire stack. And next up, we have Arnaud joining us from Skeleton Technologies to share a bit more about it. Give it up for Arnaud.
Thank you. Thank you very much. Thank you, everyone. Okay. The time is already started. Okay, it's great. Yeah.
Okay. Any highlights?
Sorry, for the from the event?
Yeah.
I mean the dinner, the investor dinner 2 days ago was really nice indeed. Yeah, it's unfortunate I'm mentioning an event that was relatively private, so not everyone could attend it. But no, the event is excellent. I participated as well to the events on defense that you organized in February, so I can really recommend all the events organized by this team. So it's really good. Yeah.
Truck in the whole sea. That was very, very impressive to see. Fully autonomous trucking. Yeah. They actually have a bit of an issue because they can't get their truck out of the building tonight, and they will see how they disassemble it in time.
I think that's then stay for the after party, and then you'll actually see that live.
Exactly. Very good.
All right, so ready to start now. So firstly, before I start, who's already familiar with skeleton technologies? Nobody. So this is great. I'm actually very happy to come and show you a little bit what was our journey was, because although I'm joining today to talk about systems of air performance, actually we have started as a materials innovation company. So really an example of a deep tech company which started from fundamental research into new materials, but now has developed into a fully integrated power systems company for AI infrastructure. So, but first, which problems that we are solving now? It's quite known, and I think a lot of people have actually addressed this topic in the panel discussions. It's quite known that AI has a power problem. AI power has become the bottleneck in the deployment of AI infrastructure. This is something which was understood already for a long time, but now a lot of hyperscalers are realizing that this is what is going to prevent, or this is going to block their own expansion of their data center infrastructure. All the hyperscalers are investing massively, so more than $660 billion of capex are going to be invested in 2026 by US hyperscalers. But the truth is that actually a lot of these announcement investments are going to only be on paper if they don't solve the power issue. Because right now, in many areas in the US, people are and companies are investing data centers, purchasing GPUs, but in reality, they cannot connect the data centers to the power they need. So you've got example, especially in San Jose, of data centers which are remaining idle because they don't have access to power. So this is really something that is becoming a major issue. Data centers are requiring enormous amount of power and energy, city scale. In the next 5 years, it's known that data centers are going to have in total the same energy consumption as the country of Japan. So this is something that is creating a lot of issues. As you can see here, new hyperscaler targets are like 1 gigawatt of power in the AI compute. So this is the equivalent of a city of 1 million inhabitants. And last but not the least, the grid cannot keep up. It was already known with development of renewable energy that grid needs to be modernized. Grid needs to become more decentralized because renewable energy can fluctuate. But now, with all the input and the peaks of power generated by data centers, this is going to become even more important. So it's quite clear that countries that are not going to be able to offer energy and power solutions are not going to be in the AI map in the future. So this is an essential bottleneck that we are solving. This is what we're doing at Skeleton. We're helping solving those 3 issues of high capex investment, power scale, power needed for data centers, and grid connection, grid power needs. But before explaining how we solve it, first, how we started. We started as a materials company. This is absolutely the thing that is not the sexiest industry and sector to invest in, actually, when you look for investors. Even worse than this, we started as a materials company from Estonia, and not even from the capital city of Estonia, from Tartu. So our material, which we call curved graphene, was developed and eventually patented at the Tartu University by four of our scientists, who are the co-founders of Skeleton Technologies. This material has specific properties. So firstly, it's what allows us to have the highest power density in the market for our supercapacitor cells, because it's extremely porous materials, which has conductivity properties, which allows to have this power density. It's also this material that we use, which allows us not to need any critical material. Our products don't need lithium, don't need cobalt, don't need manganese, none of those. So it's not only with no critical material, no toxic metal, but also unlike other data centers, even unlike other cells, supercapacitor cells, even more power density. So this is something that is absolutely crucial. Power density, it means that you can store much more power with a much faster reaction in a smaller cell format. And this is something that is critical in the field of data centers. So over the years, we have developed this raw material. The raw material, we're now using it in the cells in the modules, and then up to the power system, to the full power systems. This is something absolutely unique, which no other company is doing. This full vertical integration, starting from the material up to the full power systems, including solid-state transformers, including battery backup units, etc. And we do it all of this with a fully European value chain, with no dependency on China. But if you take some of the competitors we have, some of them do cells, LS Materials. Some of them integrate cells into the power systems, like Vertiv and Delta. But no, on our side, we always wanted to be fully vertically integrated, because the highest performance at systems level is enabled by this expertise already at the cells level and even at the materials level. What we have developed at systems in data centers is, again, quite unique, which allows us to work directly with the hyperscalers, with in-rack solutions straight into the white space of data centers, in order to absorb directly and do the peak shaving directly at the source, at the GPU level. So this is what we're doing with some of our products called a graphene GPU. But we're also working at the UPS level and at the grid level, which allow us not only to work with the hyperscalers, but also with the energy companies and grid companies. So we have developed the entire set of power solutions to offer all of the power systems needed to operate data centers in a much more efficient way. So this is what we've been doing, starting again from a materials innovation company. But the issues we're solving are actually not only in data centers, because as you know, as was said in the introduction, a grid also needs a lot of power systems, because renewables can fluctuate, and therefore you need to be able to integrate this intermittent electricity into the grid. So the fact that our products can react extremely fast, in microseconds, is what allows us also to work in the grid business. But given that a lot of companies in that conference are also doing defense, actually, we're also solving a lot of issues in defense, because nowadays modern defense systems are becoming essentially a bit like small data centers. Because when you have a land system, like when you have drones, when you have a modern tank, that have to integrate radars, sensors, jammers, all these subsystems all together, they create peaks of power that require power quality solutions and peak shaving solutions. Which is why on our side, the main business we are in are AI data centers, grid, and defense as well, and all of this while having a fully European value chain. Why Europe should care is that because right now, when you invest in AI infrastructure, concretely, it means that you are using electricity, so you're using the resource produced in Europe, and you're transforming it into intelligence. So if Europe and if European companies do not manage to have their own technology powering AI infrastructure, and if we just let all of this done by the US hyperscalers, it's trillions of euros that are just going to leave Europe and go straight into the pockets of the US hyperscalers. AI revolution is about physics. It's a physical revolution. It's not about software, not only about models, something. So the countries and the companies that are going to be on the AI map are only the ones who are going to be able to power this revolution and supply the entire infrastructure. So this is really about this. AI has always been about energy and power. We forgot it for many years, but I can say that the era of software only is fully over. Now AI is physical, and we need to be able to power it with European technologies. Thank you very much. Thank you very much, and I think we have time for at least one question.
Catch a taxi, but if we have time, that's great.
Thank you.
Any questions from the audience? There we go. Yeah.
If you enable AI revolution, then what role does AI play in your manufacturing process, or is it optimized in a way that AI is redundant?
Yeah, absolutely. So indeed, so we have an approach where obviously we have a fully digitalized and fully automated factory. Our largest factory is in Leipzig, and we use actually all the solutions, digital solutions from our main investor, which is Siemens Digital Industries. So the whole process is fully automated, and indeed, AI is now being extremely instrumental in order to really choose the right materials to use, to assemble and transform our own curved graphene in order to select the ones that can help us obtain the right properties. So indeed, for materials perspective, AI actually is now extremely, extremely critical.
All right. Thank you very much, Arnaud.
Thank you.
I'll take over. All right, so we've talked about how we make storage, how we recover it, and how we balance it. But the fourth piece is something that no one really wants to talk about until something goes wrong. And because the European grid is, we invested a lot to make it smart, inverted commas, over the last decade, but we need something protecting it. So now, please help me introduce Markus Flitsch, CEO and co-founder of Terra Quantum. Here you go.
Yeah, thank you. Also for those who still sit here, I think it's kind of the last presentation. So I'll talk a little bit about quantum and what it has also to do with, our energy system. First of all, no quantum presentation without Schrödinger's cat, right? Quantum will be the most disruptive technology, thought it was there, will be the most disruptive technology for the next decades to come. Why is that? Because this technology follows an exponential speed up. The quantum computer will show an exponential increase in compute power with the growing number of qubits, not bits anymore. And this triggers in particular 2 dimensions of disruption. The first one, by the way, the clock is not counting backwards, but I hopefully will, you say stop. It triggers 2 dimensions of disruption. The first one is actually the performance dimension. Everything which has to do with complex big data analytics, optimization, simulation, machine learning will be blown away by quantum AI, so quantum algorithms on a quantum chip. Why does that matter for the energy system? Well, AI is in an energy dead end, right? There is no real, exponentially harder challenges which we would be able on a large scale to deliver with classical AI and classical energy consumption. So we definitely need a revolution or a disruption how we use AI. The next dimension first comes as a threat, the security threat. Every classical encryption, regardless of symmetric or asymmetric, your messenger, your email, your cryptocurrency, your credit card will be hacked by a mature enough quantum chip. So the whole world needs to migrate, and that's the flip side of that coin, and a good business model for quantum companies is to protect IT infrastructures in the quantum age from an attack of a quantum computer. Very shortly, only on that first dimension, AI performance. We can, and that is something which I want to bring across. If you think quantum is, 10 years down the road, it's not. We use quantum AI, quantum algorithms already today to increase performance for, e.g., portfolio optimization in banks, but also for optimization of the grid, e.g., for large renewable companies. That's why this matters also on the AI side. And very briefly, only because I think that's quite interesting, it is fundamentally different. If you think about, what we have today, the large LLMs, for instance, they are coming to a limit of what they can deliver. E.g., there are exponentially more molecular fragments in the universe which you can put together to form something meaningful than there are words in the human language. That means if you want to, tackle exponentially harder problems, you definitely need quantum. And the game changer is also in the fact that all these LLMs are completely deterministic. They are rules-based. Never think that there will, classical AI systems on a classical computer will create really an intelligent, creative system in the way the human brain works. But this is very different with quantum, because the underlying quantum physics actually is non-deterministic and non-causal. So here you really not only open an exponential window for better performance, you also deal with a system which really works like the human brain, as this is not a classical computer, but a quantum computer. Now I come to that second topic, which is very vital also to the energy infrastructure, and that is quantum cybersecurity. All classical cybersecurity measures will not be sufficient to protect our infrastructure. Indeed, the US authorities estimate that 2030 will be the year where we potentially should expect the so-called Q day. That means that day when first elements of classical encryption and classical security will be hacked by a mature enough quantum chip. Most probably RSA, which e.g. runs our credit card system. And that's why the US authorities have also set the first standards in the US, so-called PQC, post-quantum cryptography. In the US, 250,000 mission-critical infrastructure corporations, including energy companies, have to migrate towards these PQC standards. So that is why quantum cybersecurity is a mission-critical also to secure the energy system of the future. I'm not going into the details of that, but what you have to think about if you, e.g., secure a grid or an energy infrastructure is you have to make it much harder to get into the system, and this is by using more complex algorithms which you have to implement, but ultimately you need a physical protection of your IT infrastructure that is so-called QKD, quantum key distribution, which really is the end game in cybersecurity, as a system which is QKD protected cannot be hacked anymore, even not with the strongest quantum machine out there. We are a little late, so probably we have time for 2 or 3 questions, which I like much more. But to sum it up, both dimensions, better performance by quantum systems, e.g. to stabilize the grid, and quantum security systems to protect the infrastructure will be vital for the whole energy industry. Thank you.
Thank you. So we actually have a bit of time for a few questions, if you're up for it, Markus.
Of course.
So, perfect, we're just getting the microphone. Any questions from the audience?
Maybe a question. So I'm not an expert in this. It just came up to me because you talk a lot about energy consumption of the normal way of computing. So what's the energy consumption for the quantum computing?
Very good question. As you know, we'll have millions or billions of it, and obviously the task we perform will even grow exponentially larger problems, e.g. drug discovery or so. This is a very valid question. The thing is that, yes, for current quantum chip hardware, e.g. superconducting chips, they have to be cooled down to the absolute zero, which requires a lot of energy. One might think that quantum computing will actually increase, the energy dependence of AI. But that's only half of the equation, and the second half is a much more positive one. I mean, quantum computers, once they are really mature enough, will perform calculations where classical system needs billions of years in seconds, right? So the net of that equation is that quantum machines will use much less energy, much less energy for complex analytics than classical infrastructure. So therefore, the net result of migrating towards quantum systems should actually be very positive, meaning much more with less energy.
I actually have a question, if no one else wants to go. You're a fairly large and advanced company already, but to unlock the next stage of growth where you want to get, what is something that keeps you up at night? What is a big challenge that you yet still have to master?
For us as a company?
Yes.
Well, I mean, we are indeed well advanced, and obviously the major growth driver will be maturing of the industry. So the quantum hardware, the quantum chips have to further mature because we can't do everything yet with quantum machines. These first generations of quantum machines, you can do exciting things, get a better performance, but to tackle, material science, really personalized medicine, we need stronger quantum chips, and therefore I, of course, hope and do foresee also that the maturing of the quantum hardware of the quantum chips will further progress. That is one dependency which we have, but I'm pretty confident about it, so that doesn't keep me up at night. And what keeps me up at night, though, is being a European citizen, and that is a deep tech conference here, particularly also focusing on making deep tech successful in Europe. For us, the biggest market today is already the US, and this has the strongest growth. So what keeps me up at night as a European citizen is, will quantum be the next deep tech discipline where we lose the race in that global concert? And I think there are warning signals that this actually might happen, and it shouldn't.
Thank you. I think one more question. Thank you.
In terms of energy use cases, do you have a specific beta user right now that you're working with, or partner that you're working with, that you're surprised and want to celebrate early wins of what you've done together?
Yeah, that's true. We work for a few companies, and I would take it a little bit more general, where we do more with less. And one example is, e.g., we work for a large renewables company, that this name I can't disclose, which is where we optimize the grid, where we do the data analytics, where they channel in a lot of fluctuating renewable power, and we kind of stabilize that grid system, which makes it much better performing. Also, time series prediction for some of these is much better using our quantum algorithm. That's one use case. The other is for doing more with less. Is we work for POSCO. POSCO is the largest steel manufacturer in the world, actually, or one of the largest. And they have these ovens where they produce the steel. So there's a lot of sensors in this, and you have to, optimize how you, put in the gas, how you heat up the different things of that oven. And we also used here quantum algorithms to make it much better performance, to produce the same output, better quality with much less energy. That's another use case.
All right. Thank you, Markus.
Thank you.
I'll take that for you. All right. Wrapping up all these four very different companies is obviously a bit of a challenge because it's a very broad space. But that's also why I love my job, at least as a tech and energy investor, because you talk about the European sovereignty, AI sovereignty, about electrode manufacturing and production at the same time as then security. And when I thought about some takeaways, I think a few, or one that definitely stood out to me today, is that it's not just about the cost of an electrode, but the cost of a useful electrode. At what, when it is available in the right place, what materials it is made of, and especially, is it secure? Another one that especially we talked about during the Scilab presentation was about the sovereignty of Europe, and that recycling is not a sustainability question anymore, but a supply chain question. And potentially the last takeaway, I'm not sure about the numbers, but potentially the biggest hidden cost actually of the European energy system right now is a security failure that has not happened yet. So help me in thanking all the speakers that we had today. 2 of them are still in the room with us. And yeah, let's hear it for them.